Welcome to the session. I am Michael Liu from the Chinese University of Hong Kong. The title of my talk is An Intelligent Data-Driven Paradigm Towards Cloud Reliability. We first introduce a background related to cloud and cloud reliability. Then we elaborate the following few tasks in order to achieve cloud reliability: log analysis, KPI analysis, service dependency, and outage prediction. Finally, we summarize this talk. Modern software systems provide various services to our daily lives. In particular, many such software systems are hosted in cloud to provide their services. Cloud adoption by industry is constantly arising, and cloud revenue continue to enjoy an impressive growth, as predicted in this forecast table to reach $354 billion by 2022. The most important infrastructure of cloud computing is the data centers around the world. Data centers are huge hardware and software systems with high-speed interconnection networks. The tremendous complexity of data center operations brings major reliability challenges. Because many services are supported by the data centers, if an outage occurs, a large range of users might be affected. For example, according to Lloyd's report, a major failure that brings cloud outage for 3 to 6 days could result in a total failure loss of 19 billion revenue, most of which will not be covered by the insurance. To this end, cloud resilience is very crucial. State-of-the-art cloud reliability is motivated by service level agreement with 5 to 6 nines of availability and requires high degree of automation. Unfortunately, cloud failures often occur to major cloud operators. Cloud reliability issues are mainly due to the fact that tough cloud failures take a long time to mitigate manually. They improve large revenue loss imposed on the company and harm customer trust and company reputation, and it will affect everybody's daily life. Cloud failures are often software-induced or software-related. Traditionally, software reliability engineering, or SRE, aims to solve software reliability challenges by providing simple reliability models to track software failures. My handbook of software reliability engineering, published 27 years ago, examined this process and introduced the techniques to improve software reliability, including fault avoidance, fault removal, fault tolerance, and fault prediction. This traditional analytical approach is not enough for today's complicated cloud software anymore. We need a new term called site reliability engineering, also abbreviated as SRE, to tackle new reliability issues of the cloud software. The question is, how do we perform this new SRE properly? We know data-driven AI techniques with machine learning models have been applied in many domains. This popular approach includes 3 major dimensions: data, models and paradigms, and finally, tasks. In computer vision domain, a representative data set is ImageNet with many models and tasks. There are also natural language processing domain and the code-based analytics domain with their own data, models, and tasks. Regarding data-driven AIOps for clouds, in our concern, we should ask the following question in these 3 dimensions. In the data dimension, we ask what data to collect in the cloud. In the tasks dimension, we ask what tasks should be pursued for cloud resilience and cloud reliability. Finally, we ask what models and what are the paradigms. To serve various users, cloud providers provides the flexible infrastructure containing 3 major layers, which generates heterogeneous data. The infrastructure includes application layer, platform layers, and finally the infrastructure layer. Besides cloud providers, they provide customers service to collect most incidents, outages, as well as the dissatisfaction from the users. They transfer feedback to the on-call engineers. On-call engineers inspect the status of the cloud and discuss the problem as well as a solution. And this process will generate instant tickets. To get more insights, on-call engineers need more cloud status from the logs, from the metadata, also from the topology, and finally, the alert generated in the cloud. They are collected in various cloud layers as being shown here. So this will lead to our discussion of AIOps for the cloud resilience, which is a data-driven AI approach. We examine the following data sources. Log data contain application logs, system logs, microservice trace. Metric data includes utilization of CPU, memory, disk, and network utilization, as well as the application KPIs. Topology refers to the cloud architecture of application layer, service layer, and infrastructure layer. Alerts are data generated by certain rules. And finally, incident tickets include reports, war room discussions, and chat messages. As we mentioned, traditional SRE employs 4 tasks: for avoidance, for removal, for tolerance, for removal, and for prediction. For cloud resilience, the 4 tasks are roughly changed to anomaly detection, failure diagnosis, root cause analysis, and failure prediction. In a nutshell, data-driven paradigm for cloud resilience and cloud reliability can employ 5 kinds of data to solve 4 new SRE tasks automatically. As a result, this slide highlights the overall picture of my talk over various technical contents, including log analysis, KPI analysis, service dependency, incident management, and outage prediction. The presented techniques utilize data resources from low level to high level, and the associated tasks is from easy to hard. We began with log analysis, which enables anomaly detection. We should first conduct log parsing to transform log raw data to a structured format. To do this, the log analysis AI cloud understands the event evident by the log. To perform anomaly detection on the log, a general framework is to first apply feature engineering, then train a model with features extracted from the logs, and finally infer anomalies with the model. There are many log anomaly detection methods following the same framework. Most of these methods belong to traditional machine learning algorithms like clustering, support vector machine, classification techniques, and frequent pattern mining algorithms. Besides, some papers discuss how to utilize deep learning models to conduct anomaly detection from the log sequence. This is an overview, classification, and comparison of these methods in a survey papers recently published. The next task is to use metadata for anomaly detection, which is termed KPI analysis. An example of metadata is KPI, which is one of the most important data in the cloud, which is leveraged to monitor runtime information of a machine like network traffic, response delay, CPU usage, so on and so forth. They can help us to understand health status so we can conduct anomaly detection over the KPIs, which may reflect the real anomaly within the system. For example, a simple spike in CPU load and network inflow may indicate some anomalous status. They are typically univariate KPIs and multivariate KPIs. The anomaly detection of these two kinds of KPIs differ. For univariate KPIs, each of the KPI is used to monitor a specific component, for example, CPU load. But these components are coupled together, which become multivariate KPIs. In most cases, there are fewer anomalies when examining multivariate KPIs, and the parts identified as green are actually normal. Due to lack of manual labels, unsupervised anomaly detection is often required. The intuition of anomaly detection is as follows. Many machine learning-based anomaly detections follow the same framework. It consists of two phases. In the beginning training phase, we use sliding window to generate data samples. For each sample, we split the KPIs to the two parts, the preceding observations in black and the next observation denoted in blue. In the detection phase, we compare the difference between the prediction as well as the ground truth. If the difference is obvious, then the anomaly is flagged. For example, in real case, only rare combination of the states in different category indicates anomaly, such as a red part. Log and KPI can also be correlated to enable failure diagnosis and problem identification. Different patterns within the log may indicate different types of problems, but these problems may affect the KPIs in different ways. As a result, we are able to first classify the types of problems in the logs and correlate them with the degradation of the KPIs. We evaluate the method on real Azure data. 3 large-scale data sets were investigated. Our method called log3c performed the problem identification task with high precision and recall comparing with SOTA approaches. With topology information, service dependency in the cloud allows root cause analysis. A production cloud may be built on multiple services. When a failure happens on a dependent service, cascading failures of other services may happen. Moreover, when performing recovery, an awareness of the service dependency may slow down the process. In public outage reported by AWS, we found that 5 out of 13 AWS outages are related to service dependency. However, current practice simply defines the dependency as a binary relationship. That is, dependency either exists or it doesn't exist. But it fails to consider the degree of dependency between services, which is caused by different fault-tolerance mechanisms. Hence, we propose the concept of aggregated intensity of dependency. And the novel framework is called AID to measure that. It consists of 3 parts: candidate selection, service status generation, and intensity evaluation. The input raw data is a trace log. In today's industrial practice, calls between services are generally recorded by a tracing mechanism. When a user sends a request from outside, the request will be given a trace ID. Processing a request requires different service collaboration. Each call between different services will generate a span log, as shown in the left figure here. Each span will record the name of the parent service, call duration, call result, and other information. The right figure is a span generated by an open source microservice benchmark. The first step is to generate candidate call pairs. The purpose of this step is to find all the call relationships that need to be evaluated. One can complete this step by traversing all the spans. If there is a centralized call database in the cloud system, you can also directly query the database. In the second step, it is generated by the service status sequence. Each service has 3 types of status indicators, namely call times, call duration, and error rate. And we can process them accordingly. Based on the status sequence, we can measure the intensity by comparing the similarity of the sequences. Alert aggregation in AIOps can also enable failure diagnosis and root cause analysis. To assist an engineer in failure diagnosis, 2 tasks can be performed, which are alert aggregation and root cause recommendation. As shown in this figure, when service A encounters a failure, the failure may propagate to its neighboring services. Incident aggregation can separate these incidents from other irrelevant ones as the blue ones. So engineers only need to focus on the red incidents, which are the more important ones. To address these challenges, we propose an incident management framework based on graph representation learning. As shown in this figure, our framework consists of 4 steps. In the first step, we detect the incident bursts, which often indicates the occurrence of cloud failures. In the second step, we use more fine-grained cloud monitoring data, that is KPIs, to auto-complete the graph, which recovers the big picture of the failure. Next, we leverage graph representation learning to learn a vector of each incident, which encodes its interactions with other incidents in temporal and topological dimension. Finally, with the representation, incident aggregation and root cause recommendation can be naturally performed. The evaluation on real data set generated by a top public cloud shows our approach can achieve obvious improvement compared with other methods. The AIOps application, the last one I will present here, is the outage prediction, where the alert data can be employed for failure diagnosis and failure prediction. Cloud components usually trigger some alerts indicating anomaly, behavior, or failure. But due to fault-tolerant architecture, users are unaware of such alerts. So users may be happy when some incidents or failure occur in the cloud systems. However, when the situation becomes worse, some severe fault may happen and the cloud could become unavailable, causing cloud outages. To prevent such a cloud outage, this paper shown below here presents the first detection of some of the alerts and make prediction on the possible outages. It utilizes a Bayesian network in order to keep track of the dependency. For example, the website application outage, when detected, is highly related to time shifting, storage testing, and website servicing. So after data analysis and augmentation from the Bayesian network, a classification model can be trained to link the observed alerts to the cloud outages. And they got a very good result, as this shown in this table over here. So in this talk, we introduce the task list in the bottom for different goals in order to achieve cloud reliability, which is actually an integrated data-driven paradigm. So we can draw the following conclusion. Data-driven approaches are promising in today's cloud intelligence and the AIOps. Cloud reliability as a result call for new software reliability engineering approach in order to apply data-driven models and paradigms. And current approaches for reliable AI ops are ad hoc, specialized, and vertically integrated only. So I will recommend that more benchmark data sets should be collected, and this will require collaboration among industry and academia. And I believe this joint working together is the direction in order to make AI ops impact to our society. Thank you for listening to this talk.